And this is my presentation on lab number 4 about bar magnets. First, we have our introduction. Okay, so what was this lab's purpose? Well, we wanted to find the magnetic moment of a magnet as well as its magnetic field. The tools we used were a bar magnet, a magnetometer, which was just an app on our phone, and a measuring stick to measure the distance of the magnetic field. The physics principles we used were the Biot-Savart law, the magnetic field of a dipole, which is just a derivative of the Biot-Savart law, and the distance dependence of a magnetic field of a bar magnet equation. The lab's results were we were able to find the magnetic moment and net magnetic field of the magnet, and our predictions slightly differed from the glow script model, but they were fairly similar. Okay, so next we have the experiment observations. Okay, so defining our system. So our assumptions are that the magnetic field will decrease the further you move away from it, as all fields do, and that the bar magnet is a dipole, and that there are no other fields acting on the phone, such as from our electronic devices or anything like that. And the system is just the bar magnet, and anything else is the surroundings. So running the experiment, first we wanted to find where the magnetometer actually was in the phone. So we positioned the phone perpendicular to the magnetic north and slid it along the measuring tape and marked with tape where there was the maximum magnetic field for the x and y axes. So we slid it first vertically and then horizontally. And by doing this, we were able to actually mark using tape where the magnetometer was. Next, we actually wanted to find the net magnetic field coming from the bar magnet. So doing this, we first set and found where the magnetic field was 0. Then we slid the phone horizontally and vertically until we found where the net magnetic field was 100 microteslas on the phone's magnetometer. And then we recorded the net field for each component, and then we repeated this 3 times. And by doing this, we found that the magnetometer, the farther you got away, the smaller the magnetic field was. And when the magnetometer was closer to the magnet, the magnetic field in the x direction increased. So these were our final discoveries. So we found that the net average field was 0.0000547 teslas. And when graphing this, we see that there's obviously a negative slope, and so this can be modeled by an equation of y equals negative 2.7192x minus 13.948. And we're able to actually use this to find n, as n is just the slope, so negative 2.719, and ln of k is equal to negative 13.948. So doing this, finding the log, we get that k is equal to 8.759 times 10 to the negative 7th. And this is useful because then we can set this equal to the Biot-Savart law, which we can then find the magnetic moment for the magnet, which is 4.3795 using algebra. Next, we have our computational model. So we plug in essentially everything we found previously in our observation. We use a function to find using the Biot-Savart law, and then we plug in our distance as just 0.2 so we can have a better viewing, and our scale is 1000, and then we plug in for each axis the distance away from the magnet, as well as we plug in the magnetic moment, or mu, that we found previously. Here, we are just creating arrows representing each viewing point on axis and perpendicular to the magnet. And we also know that the perpendicular distance that we found earlier is 0.1843, so we plug that in. And then also use the Biot-Savart law to get the magnetic field at 45 degrees. When we run this model, we get that the perpendicular field is negative 5.47 times 10 to the negative 5th. We also get d is equal to 0.260687, and the field at 45 degrees is 1.23 times 10 to the negative 5th, 3.708 times 10 to the negative 5th, and then when we take the net of that, it's 3.908 times 10 to the negative 5th teslas, which is slightly less than the net field that we found earlier at 5.48 times 10 to the negative 5th teslas. This discrepancy could have been caused by inaccurate phone measurements or other magnetic fields such as like our phones or our computers in the surrounding area. So discussion and conclusion. What if we hadn't oriented the phone to compensate for magnetic north? Well, our measurements wouldn't be accurate because now we would have to the magnetism of the magnetic field of the Earth would be interfering with our measurements. And then if we stuck two identical magnets together, it would just essentially double the magnetic field and wouldn't really do anything else. It would just be creating a even larger, stronger magnet. All right, thank you.